Section 9.3 is on exponential growth and decay. When you have exponential growth or growth in anything, that is when the value or the quantity increases. In this case, your R, which is your common ratio, has to be greater than or equal to 1. When you have exponential decay or decay in anything, that is when your quantity or your value is decreasing. In exponential functions, that is when your R value or your common ratio is less than 1. It's going to be a fraction or a decimal less than 1. So we were going to first do exponential growth formula first. The only difference between the exponential growth and decay is that in growth there is a plus sign, in decay there's a subtraction sign because it has to be less than 1. So here the equation is y equals a parentheses 1 plus r raised to the power of t. So I broke down with the formula, each part, each value, each variable ends up equaling. Y is what you're trying to find, your final amount. A is your original amount. Sometimes it could be a original value, original amount. Sometimes we're going to get into some banking and money questions where that is called the principal value. There's several different ways. They could just say the first value, the starting value. They could say any of those things. In the second one, you have, in the parentheses, you have 1 plus the rate of growth as a decimal. So they're going to give you, like, there's a 5% increase or a 25% increase. You have to transform those decimals into, you have to transform those percentages into decimals. So for example, if there's a 25% increase, you're going to transform 25% into a decimal, and that would be 0.25. If it was 5% increase, that is going to transform into 0.05. Remember that you take your value, the decimal place being here, and you would move it over 2 decimal places. Fill in any holes with zeros, and then you have the decimal form of that percent. It's going to get added to 1. It's always added to 1 because that's what's going to put it over the value of 1 in order to show that there is growth. Time can be different for any problem. Time could be minutes, it could be hours, it could be days, it could be years. Just pay attention to whatever the problem is and whatever the story may be. Notice here we're not subtracting 1. It's not time minus 1. Okay, that was with geometric sequences, and that was when you had to find a future term. Now when we're talking about these types of problems, you're not subtracting 1 from the time. All right, so let's look at an example. It says the original value of a painting is $1,400, and the value increases by 9% each year. Write an exponential growth function to model this function. That's the first thing we're going to do, and then we're going to find the value of the painting in 25 years. So again, your equation, y equals a times 1 plus r raised to the power of t. So I don't know what y is. It tells me that the original value is 1,400. Now, my rate is 9%. 9% as a decimal is 0.09. So I'm going to write 0.09. And time for right now, because the first part of this question wants me to just write the exponential function. So as an exponential function, in fact, I won't make it x. I can just keep it t if you'd like. It can be t or x. It doesn't matter. That's the first part. Now for the second part, they want to know, okay, how much is this painting worth after 25 years? So now I'm going to plug in the 25. And you can simplify what's in the parentheses first. Maybe you could have done that in your head already. And you're going to type this into the calculator. In the calculator, we are talking about money here. So we do want to make it into rounding it to the hundredths place if necessary, because we are talking about money. So we get a value of $12,072.31. Again, the question had 2 parts to it. First, you had to write an exponential function. So that's this part right here. And again, at that point in time, at that point in the question, I don't know about the 25 years. They just want me to use variables for the t. You can either use a t or you can plug it in with an x, whichever one that you'd like. It does not matter. But I don't plug that 25 in until after that sentence. That's my second part of my answer. So when you're having to write this, make sure you don't plug the number in the first part. You're just writing the basic formula for how you would find out the value of this painting. All right, let's look at example number 2. A sculpture is increasing in value at a rate of 8% per year, and its value in 2000 was $1,200. Write an exponential growth function to model the situation. Then find the sculpture's value in 2006. So for this one, we have y equals, your starting value is 1,200. I have 1 plus, I need to make 8% a decimal, and that's 0.08. And I'm going to just raise it to a power of t because they just want me to what's the modeled function, and there it is. Now I'm going to go and I am going to plug in my time. Well, I'm not going to plug in 2006 because it's not 2006 years. The difference between the year 2000 and the year 2006 is 6 years. So we're going to type that in the calculator. If you want to do some simplifying first, you can. And again, we're talking about money. So when you're talking about money, you need to make sure you round to the hundredths place. And we get $1,904.25 as your answer when that gets typed in the calculator. All right, exponential decay. This usually has to, again, they'll talk about populations. They start doing decay is a lot of science stuff as well. It's not just money. It can be both people. We did, again, with the dogs example, populations, but it can also be money in decreasing or something's depreciating in value. So the formula is exactly the same, except you have a subtraction sign instead of an addition sign. So let's look at this example. It says the population of a town is decreasing at a rate of 1% per year. In 2000, there was 1,300 people. Write an exponential decay function to model the situation, then find the population in 2008. All right, so you have y equals a times 1 minus r raised to the power of t. So I'm going to plug in the information I have. In 2000, that's when they counted the population, was taking place. So that's my starting value is 1,300. 1 minus, now the rate is 1%. So I need to make that as a decimal, and it's 0.01. And I'm going to raise it to a power of t. That is the exponential decay function. Okay. Now, in the next step, this is where I'm going to plug in whenever they want me to find out how much population was there. It says then find the population in 2008. Once again, I'm not plugging in. I'm not going to raise this to a power of 2008. Wouldn't even, the number would be so big it wouldn't even fit in the calculator. In this case, there's 8 years have passed from 2000 to 2008. So I'm going to raise this to a power of 8. So y equals 1,300 times 0.99 raised to the power of 8. And when you do this math, now we get 1,200 and, actually I got to get the exact value when we put it in my calculator. So, sorry, we get 1199.568 and so on. Now, we're talking about people. You cannot have 1199.56 because you can't have 0.568 of a person. Therefore, we're talking about people, so I would round down, and I would say it's 1199 for this particular problem. So again, you only want to deal with that whole number and rounding down when you're talking about living objects like people or animals. All right, we're talking about fish in this example next. So the same thing is going to happen where you are going to round down if necessary in order to find out the population. So it says the fish population in a local stream is decreasing at a rate of 3% per year. The original population was 48,000. Write an exponential decay function to model the situation. Then find the population after 7. How long should that be? That should be 7 years. Don't know what happened there. Okay, so first I'm going to write the exponential decay function. My original value was 48,000. 1 minus the rate. The rate is 3%. As a decimal, that's 0.03. I'm going to raise that to a power of t. Now, if when you're asked to write the exponential decay function or even the growth function and you want to do the simplifying first and then write it like that, this is acceptable as well to write it as 0.97 instead of 1 minus 0.03. As far as your quiz is concerned, again, you are going to have multiple choice, so I wouldn't give you both of those as possible options. I'd only give you one or the other. So just know that they do mean the same thing. Now, 7 years of time, so I'm going to plug in 7 for t. And when I get that, I have 48,000.97 raised to the power of 7. Now, this gives me 38,783.177. Okay, again, we're talking about fish, so that's a living object, so therefore I'm going to round down because you're not going to count 0.177 as an entire extra fish. So I need to get an accurate count here, and that's what it would be, is 38,783. And in science, I mean, you are talking about population. In the course of 7 years, you don't know what might happen in a local stream. There could be a drought, and therefore in one particular year, the number of fish, they happen to die off more than another year. Maybe another year there is an excessive amount of rain in a stream, and therefore you have a lot more fish that are present, and it kind of averages out. So these are estimates in order to be able to find out a future population. It's not necessarily going to be an exact number, only because they're finding it's a prediction. They're saying if they continue to decrease at this rate, how many will you have after so many years? In addition, you might have the person that is counting the number of fish. I don't even know how you would count the number of fish in a stream, but whatever. That's why I'm not a scientist counting fish in streams. But whatever, the person that has to count the number of fish, they might do it in January one year. Well, the next year, maybe it's winter and they're not able to get out in January, so they don't count the fish until March. 2 extra months could mean a lot more fish or a lot less fish depending on the conditions. So those things all come into play whether or not you're going to have an exact number of fish. You just need to remember that you're going to round down because 0.177 in this circumstance does not count as a fish. All right, so going from science and population and things, we're going to go to compound interest. This is actually one of those very, very, very real-world situations that you will face at some point. And this is called compound interest. This is what you do when you've got some amount of money that you want to put in the bank. Compound interest is the interest paid on however much money you have to deposit into a bank account. You want compound interest. The more compound interest, the better, because that just means you keep getting interest. And it's compounded because not only if you put $100 in the bank, not only are you getting interest on that, you're getting interest on the interest it already has received. That's the previously earned interest. So the original amount in these problems is usually considered or called the principal value. If you were to call up a bank, they would refer to that original amount or maybe your initial deposit in the bank as the principal value. So here's our equation. I wrote it all out. A equals P parentheses 1 plus R divided by N, all raised to the power of N times T. Now, A stands for the account balance. That is how much money you're going to have in your bank account after a specific amount of time that has passed. The P stands for, that's where they get the principal amount. Think of that as your original amount money that you started your bank account with. It's always going to be a 1 plus. Now, R is the annual interest rate. Again, you're going to take the percentage that you're given and transform it into a decimal. And you're going to divide that by the number of times the interest is compounded in a year. So right below here, I gave you a little list of the four most popular, most used ways that something is compounded. If something is compounded annually, that means that you're going to divide by 1. And that means it only happens once a year. Semi-annually is twice a year, so your end value you would divide by 2. Quarterly happens 4 times a year, and that's n equals 4. And the last one is monthly. Since there's 12 months in a year, that happens, you get interest once a month, which would be awesome if that happened a lot. Usually they would only do that in really rare circumstances. Banks would do that in a rare circumstance if you have a tremendous amount of money. And that's why you always hear that term, the rich get richer. Because if you had, instead of $100, you had $100 million to deposit into the bank, the amount of interest that you would get so the banks could use your money while you're, putting it in the bank is worth a lot to them. So they would give you a lot of money. They'd be paying a lot of interest on it. Now, the exponent is the number of times compounded. So it's either going to be a 1, a 2, a 4, or 12. And you're going to multiply that by the number of years. So if something is quarterly, that would be 4 times a year. And let's say it was for 5 years. So I would multiply 4 times 5 and I would get 20. So I would raise it to a power of 20. So the exponent you raise it to is a product of the number of times compounded and the number of years that you are going to be investing your money into a bank. Now, on the flip side, it doesn't just have to be something that's your money that's being deposited, that your savings, that you're earning interest on. Unfortunately, it could work just the same way in the opposite direction. If you borrow money and you get a loan, if you are going to buy a house and you need to borrow $100,000 from the bank. Well, you're going to have to owe, you don't get to magically give them back exactly $100,000. No, the bank makes you pay to basically rent their money and use their money. So that's where you would have the same formula would basically be used depending on how they're going to charge you interest. And it's usually, unfortunately, in that circumstance, they really get you with the monthly interest. Okay, so let's look at some of these examples. First, they're going to ask me to write a compound interest function. Then I'm going to find the balance. So I have 2 parts to this answer. In the first part, it says $1,000 invested at a rate of 3% compounded quarterly. Okay, so your amount equals your principal value, which was $1,000, 1 plus, now 3% is 0.03, compounded quarterly, that's going to be 4 times, so I'm going to divide this by 4. Just the 0.03 gets divided by 4, not the 1. Then I'm going to raise this to a power of 4, and for the first part where they asked me to write a compound interest function, I'm going to ignore the 5 years for 1 second. Pretend that's not there. I'm just using this information. I'd have 4t. So that's my compound interest function. I didn't solve anything. They basically just want you to set it up. That's all that they're asking you to do. Now, I'm going to plug in that 5 into the t spot. So I have A equals 1,000. If you want to do the math here, you can. You're going to eventually have to do it. You may want to do it in separate steps rather than trying to type this all in your calculator at one time, because you have a fraction inside a set of parentheses. So it can get a little sticky if you try to do it all in one shot in your calculator. I would take it into little steps. First, do the 1 plus 0.03 divided by 4. Again, make sure you're putting parentheses around the 0.03 and the 4 to make sure that you do that before you add 1. Otherwise, you'll get the answer wrong every single time. So I have 0.0075 raised to the power of 20. So when I enter this all into my calculator, I get, and again, I want to round to the hundredths place so it looks like money. and I get $1,161.18. If you think about that, 5 years time has passed. You invested $1,000 and basically you earned $161 just for the bank holding on to your money. Now, $161 may not seem like much over the course of 5 years, but at least it's something. You didn't do anything special to earn that money. You weren't out working so many hours to earn that $161. That was simply $161.18 that you got for doing nothing other than keeping your money in that bank. Okay, next one. Now we start off with more money, so the interest is going to end up being more money when we're done. Okay, so it's 18,000. 1 plus 4.5% is 0.045. Don't go rounding anything here. Don't do anything to the hundredths. Include the decimals here. You're not going to have things that go out and are repeating. So don't round inside the problem because you're only allowed to round one time, and that's at the end of the problem. Now, compounded annually is just one time. And then I would just have 1 times t, which is t. So there is my function. Now I'm going to plug in the 6 years in order to solve. 0.45 divided by 1 is just 0.045. Raised to the 6th power, okay. 18,000, 1.045 raised to the 6th power. And that is going to give me a grand total of $23,440.68. Now, yes, that was a much bigger jump. That was a $5,440 increase. It was much, and this was over 6 years. So again, this person who invested $18,000 earned a lot more money. They earned $5,000 compared to $161. And that's simply, not only was the interest rate more money here, but in addition, it was, you started off with a lot more money. So the more money you invest, obviously the more money you're going to get back in interest. So when those big paychecks keep rolling in and you put those in the bank, in your bank account, you'll start to notice a larger increase just simply because you've got more money. That's how the world works. All right, next one. A equals 1,200. 1 plus 3.5 is 0.035. Compounded quarterly, I'm going to divide that by 4, and I'm going to have 4t. Now, this example where there's a 4 there, that came from being quarterly, not the fact that they want me to figure this out for 14 years. So A equals 1,200. 1 point, I don't know what that is. Let's see. 0.035 divided by 4. 0.0875. 4 times 4, which is raised to the power of 16. Now notice this number when I did the math of what 1 plus 0.035 divided by 4. I didn't do any rounding. This is as far as the decimal goes out. It's not going to kill you to have to use that all. Don't round inside the problem. You really would not want a bank unless they were rounding up. But sometimes they may not round up. They might round down, and you might lose a little bit of percentage, and therefore you'd lose some of your money. So you don't want to do any rounding until the very end if necessary. So here we end up with $1,379.49. All right, last compound interest one. I have the account value is 4,000 times 1 plus my interest rate is 0.03. Notice that all these interest rates are relatively small. It's not like you have, a 75% interest rate. Banks don't do that. Neither are loans. No one would be able to afford it either way if that's how much interest that they were charging you. It would put businesses out of banks out of business, paying that much money. So it's usually around the single digits is what the interest rates usually are. All right, compounded monthly, that means I'm going to divide by 12. And this is going to be 12 times t. So there's my compound interest function. Now I'm going to plug in the 8 years. I can do a little simplifying here. Let's see, 0.03 divided by 12 is 0.025. And I'm going to raise this to the 12 times 8. 12 times 8 is 96. So they put interest on this 96 times. We end up with 5,083.47. Again, make sure that you can type it in your calculator and that you can get the same answers that I'm showing you on these problems. Okay, now the last type of problem, so this is the fourth formula, I guess you could say, for this section, is a half-life. And this is solely has to do with math. Not math, it has to do with science. Math used in science is what I was trying to say. Because a half-life is of a certain substance, a certain chemical, some kind of substance that's in science that after a certain time it decays or possibly dries up. It could be a liquid, something that's in liquid form. It could be something that's in a gas form and it gets it's evaporated in the air. They'll give you the names of all these different chemicals or substances and what happens to them. So a half-life is basically when, if it was water, if I took water and after a certain amount of time, half of that water is gone. What would make water disappear would be the fact that it got evaporated into the air. So different chemicals decay for different reasons, and I'm not going to go into that because I'm not a science teacher. But that's what a half-life is. So it's always being cut in half, hence the name half-life. So the formula here is A equals P, parentheses, 0.5 raised to the power of T. Now the A stands for the final amount. P stands for the original amount. 0.5, that is always going to be 0.5. And the exponent is the number of half-lives in a given period of time. So you have to be able to calculate the number of half-lives that there are going to be. So for example, that T, that exponent, is the number of half-lives in a given period. So the first thing they're going to tell you when they're doing these problems is how long is the half-life of a particular object. Then they're going to give you a time period and you're going to divide one into the other. So for example, if a substance has a half-life of 20 seconds, in 1 hour's time period, T would equal. So I got to figure out how many times 20 seconds happens in 1 hour. Now, 1 minute, we know that would be 20 seconds into 1 minute. Okay, if I'm going to convert that, 20 seconds happens 3 times in 1 minute. Well, in 1 hour, there are 60 minutes. So I'm going to multiply that by 60. So my answer is 180. So in this particular example, I would be raising it to the 180th power. Next one, if a substance has a half-life of 4 days, in 8 weeks, T would equal, well, I got to convert weeks to days. How many days are in 8 weeks? You would multiply this by 7 and you get 56. So now I need to figure out 56 divided by 4 gives me 14. So it would have a half-life 14 times. 14 times this particular substance would cut itself in half. All right, let's do some examples. Fluorine 20 has a half-life of 11 seconds. Find the amount of fluorine 20 left with from a 40-gram sample after 44 seconds. So this is my principal value, okay? This 20 is the name of the substance that's being used. So I have 40 as my original amount. 0.5 is always going to be 0.5. Now I got to figure out how many times does the half-life occur. It's 11 seconds that each time it happens in a 44-second time period. So I'm going to take 44, divide by 11, and I get 4 as my answer. So from here, I'm going to type this in my calculator, 40 times 0.5 raised to a power of 4, and I get 2.5. That means there's 2.5 grams after a specific amount of time. All right, next one. I've got, I don't even know how to say this one. Cesium-137 has a half-life of 30 years. The original amount of cesium-137, again, the 137 you can just ignore. That's its name. That's completely its name. So don't get confused and use 137. It's just, that's what they named it. So this one has a 100-gram sample. Multiply that by 0.5. Now, 30 years in a 180-year time period. That's going to be 6 times. So I'm going to raise that to a power of 6. So for this one, what do I have? I end up with 1.5625. Now, as far as rounding is concerned, again, if this is multiple choice, just pay attention. You follow their lead. They're not going to give you, 1.5625 and also give you 1.56 and also give you 1.6 because those are all technically the same thing. So look at the answer choices and pick whichever one that goes best. For our sake, usually we do round to the hundredths place, just that, which is 2 places after the decimal. But this is fine for right now, so don't get hung up on the whole rounding thing right now. You're not going to have any repeating decimals that you have to keep going on through. All right, last one. Bismuth 210 has a half-life of 5 days from the amount of bismuth 210 left from a 100-gram sample after 5 weeks. All right, so my 100-gram sample is first times 0.5. So it takes 5 days and in 5 weeks. So I got to figure out how many days are in 5 weeks. That's 35 days. Out of 35 days, every 5 days is a half-life. So that's going to give me 7 times that this is going to roll over and get cut in half. So I'm going to type this into my calculator, 100 parentheses 0.5 raised to a power of 7. And this one we get 0.78125. Now, we are going to, I'm going to have you practice a couple of these problems. So before we return to Zoom, I want you to do numbers 1 through 9. Try and set them up as well as calculating them out into your calculator. And then we can work on those when we come back to the Zoom meeting.